Hi everyone, welcome back. In this lecture we're going to continue our review of functions, and we're going to look at in particular exponential functions and logarithmic functions, and then of course more general inverse functions as well. The pace of this lecture is going to be a little bit more brisk than our future lectures in calculus related content. So let's get this review started. We're going to be interested in looking at exponential functions, so let's recall some of the properties that the exponential operation has. If a is a number, positive number, not equal to 1, and x and y are any real numbers, then if I take a, raise it to the power of x plus y, that's the same as taking a to the power of x and multiplying by a to the power of y. This is something we typically use in the form of, well, suppose I had 2 to the power of 3, and I was going to multiply that by, let's say, 2 to the power of 4. Well, you may immediately remember this rule that says you just add the exponents. Now, why do we add the exponents? Well, 2 to the power of 3 just means 2 times 2 times 2. 2 to the power of 4 means 2 times 2 times 2 times 2. And so now I've got a collection of 3 plus 4 2's. So that's the same as 2 to the 3 plus 4, or 2 to the 7. Now, of course, this example involved integer exponents, and these properties here I'm listing for the exponents being any real number, but they're coming from the fact that these things were true for integer valued exponents. Similarly, for division here, a to the power of x divided by a to the power of y is the same as a to the power of x minus y. In particular, in the case where x is 0, we have that a to the negative y is equal to 1 over a to the y. So a negative exponent just means reciprocal. A to the power of x raised to the power of y is just a to the power of x times y. Again, you could see y by just doing a quick example with some integer values. I could say 2 to the power of 2 raised to the power of 3, for example. What does this mean? Well, it means it's 2 times 2 raised to the power of 3. So that means it's 2 times 2 times 2 times 2 times 2 times 2. And there are 3 groups of 2 here, so it's 2 to the 2 times 3, or 2 to the 6. And similarly, we get a times b to the power of x. It's just a to the x times b to the x. And this is just due to the fact that we can multiply in any order. Multiplication is commutative, so I can multiply all the a's together first and then all the b's together second, and that results in what's on the right-hand side of the equation. Okay, so that's just a quick review of these exponential properties that we'll be using again and again and again. So let's sketch the graphs of these following functions. F of x is equal to 2 to the x, and g to the x is 3 to the x. Typically, when we go to sketch the graph of a function, we hopefully can remember or recall what the general shape of these things are, and then maybe use some transformation properties to sort of get the right position for the given function. Here, let me just recap what we would do, sort of the lowest level of approach to graphing functions, and that's really just to say, well, try to figure out a table of values for it. So here's our first function, f of x is equal to 2 to the x. I want to get a rough idea of the shape, so maybe I'll just start taking different values, maybe negative 2, negative 1, 0, 1, 2 as inputs. So that's 2 to the negative 2, or 1/4. 2 to the negative 1, 1/2. 2 to the 0, that's 1. 2 to the 1, that's 2. And 2 to the 2, that's 4. So we start off with really small numbers. We pass through 1 when the x value is 0. And then we start taking off, and the numbers get bigger and bigger and bigger. So it looks something like this. And then it sweeps up, and it starts taking off. So that's our f of x is equal to 2 to the x. A couple of sample points here, maybe. So 1 has a value of 2, and then 2 had a value way up here of 4. What about the next bit? Well, that was this g of x is equal to 3 to the x. So g of x is 3 to the x. 3 to the negative 2, that's 1 over 3 squared, or 1 over 9. This is 1 over 3. 3 to the 0, that's still 1. this becomes 3, and this becomes 9. So 1/9 is much smaller than 1/4. 1/3 is smaller than 1/2. So our function is going to be starting below the graph of 2 to the x. They both pass through the same point, 0, 1. But then beyond 0, the exponential function of base 3 takes on bigger values than the exponential function of base 2. So that's our g of x is equal to 3 to the x. And so what I just want to get from this is just a quick review of general shapes of exponential functions and how they relate to one another. So here the base 3 was bigger than the base 2. So when the x values are bigger than 1, or sorry, bigger than 0, the exponential function of base 3 should sit above the one of base 2. But when x values are negative, the exponential function of base 3 should sit below the exponential function of base 2. What about the exponential function of base 1/2? Well, here we can make a quick observation that 1/2 is the same as 2 to the negative 1. So this is really the function 2 to the negative x. But this is just then f of negative x, where f was the exponential function of base 2 written above. So what that means is big F is just a transformation of the little f function. It's been reflected across the y-axis, across the vertical axes. So our sketch we can immediately get from our sketch of f of x by just reflecting it across the vertical axes. So it looks something like this. So that's f of x is equal to 1/2 of x. And again, it passes through 1. So what I did was I took the graph of f of x equals 2 to the x above and took its reflection across the vertical axes, and that gives us our graph of 1/2 to the power of x. The key thing to note here, and this is going to be the important part when we start to get into the concepts of calculus, is what happens when x gets really big? Well, I'm taking 1/2 raised to the power of really big numbers, and we can see, oh, those are getting really small. Those are getting closer and closer to 0. What happens if I take 1/2 to the power of a really large negative? Well, that means I'm heading off in this direction, down the negative x-axis, and our function values are getting bigger and bigger and bigger. So as x gets big in the negative, the function values get big in the positive. These are the kinds of things we want to be able to do when we get to the concept of a limit in calculus and other concepts as well. We're going to be dealing with that quite a bit. So having a good picture of these functions is essential for being able to answer questions such as those in the future. Okay, so let's just continue looking at examples of exponential functions. We've got f of x is equal to 4 to the x. What is f of 2? Well, that would be 4 squared, or 16. What's f of negative 2? Well, that's 4 to the negative 2, but a negative exponent means we're really just looking at the reciprocal, so that's 1/4 squared, or in other words, 1/16. What's f of 1/2? Well, that's 4 to the 1/2. And what's 4 to the 1/2? Well, that's just the square root of 4, so that would be 2. Now you may say, well, why is 4 to the 1/2 the square root? Maybe you learned that, you knew it, but you want to know why. Okay, why is the power of 1/2? Why does that mean square root? Well, just as a side note, let's just see. We've got 4 to the power of 1/2. I want to know what that number is. Well, notice that I could square that. If I square that, I can use the properties of exponentials that say, well, it's just the product of the two exponents. 4 to the product of the two exponents, that's 4 to the power of 1/2 times 2 is 1, or 4. So what does that mean? It means that this number, 4 to the 1/2, has the property that when you square it, you get an answer of 4. So that tells us that 4 to the 1/2 has to be the square root of 4. Or in other words, it's 2. And here, 4 to the 1/2, this is a positive number, so that's why we're looking at the positive root. Okay, what's next? Well, what about f of 3/2? So f of 3/2, that's 4 to the power of 3/2. Well, we could write this as 4 to the 1/2 to the power of 3. Using properties of exponents again. 4 to the 1/2, that's the square root of 4, that's 2, so that's 2 to the power of 3, or 8. So here we can work out 4 to really the power of any rational number by just noticing that the denominator just tells me what root I need to extract, and the numerator of that input will tell me what power I need to take it to. So here's the big question. What if we were to ask 4 to the power of square root of 2? What would that be? Well, this is a big question because we know how to deal with rational exponents. So we know how to deal with things of the form 4 to the power of p over q. This just means take the qth root of 4 and then raise it to the power of p. We know how to deal with 4 to the rational number p over q for any rational number. But what does it mean to take 4 to the power of root 2, which is an irrational number? What does that mean? What does it mean to take the root 2th power of 4? Well, the way we deal with this is we use the fact that we know how to answer the question of 4 to the power of a rational number. We know what that means. We know how to make sense of that. How do we make sense of 4 to the square root of 2? Well, what we're going to do is we're going to say, let's look at 4 to the power of rational numbers, which we know how to deal with, but where the rational numbers become better and better approximations of root 2. Now, if we recall, the square root of 2 is approximately 1.41421356237, and the decimal expansion continues on forever with no pattern, with no repeating pattern. So what I can do is I can say, well, I want to know what 4 to the root 2 is. Well, maybe I'll approximate root 2 as 1.4. Well, that's a rational number. That's 14 over 10. So I know what 4 to the 1.4 is. I can deal with it. It's just the 10th root of 4 to the power of 14. And I can work that out. That's going to be this. Okay, but we can do better. I can take an approximation of root 2 to be 1.41. And that's still a rational number. It's 141 over 100. Maybe I'll write this one in, and then it'll be the last one I write as the rational number. So that's a rational number. So I can work out its value. So I can keep going, each time taking a better approximation of square root 2, and then working out the corresponding power of 4. And we can fill in the table like this. Now you'll notice that if I scan down the values of 4 to the power of x for these various inputs of x, I'm starting to get some common decimal places. So this last one, 7.1029932, matches the one above it, but then they differ in the next decimal place. So if I want to know what an approximation of 4 to the square root of 2 is, then I essentially have an approximation here. I know it to 1, 2, 3, 4, 5, 6. Can I trust the decimal place of 2? Maybe, maybe not. So maybe I have 6 decimal places here as an approximation. If you think about what your calculator is going to do when you plug in 4 to the square root of 2, the very first thing it does is it takes an approximation of the square root of 2. It's going to use something like this to represent the square root of 2. So it's already taking an approximation of the square root of 2 as a rational number. And then it's going to work out the corresponding power of it and return to you this approximation. But we want to know what 4 to the square root of 2 means exactly. What does it mean exactly? Well, we get at it through this sort of table. This says that if I keep going, I can take this sequence of numbers as close to square root of 2 as I like. I keep taking more and more decimal places, and I can get as close to square root of 2 as I like. So this sequence of numbers, this sequence of inputs, is heading towards the square root of 2. And it turns out that these numbers are heading towards a unique number. They head towards a unique number. They get closer and closer and closer to a particular real number. That particular real number is what we call 4 to the square root of 2. So we've defined, in some sense, 4 to the square root of 2 to be the real number that we get by taking 4 to the power of these rational numbers that get closer and closer to the square root of 2. So we've defined 4 to the power of an irrational number in terms of some sequence of 4 to the power of rational numbers. Okay. So that's a big question, and it requires, in some sense, a big answer. You will, in a future course in mathematical analysis, here it's at Simon Fraser, it's Math150, you'll go a little bit more into detail into these kinds of constructions, how to make sense of expressions like 4 to the square root of 2 using the connection of rational numbers to irrational numbers. Okay, but I just wanted to point that out, that this is a bit of a subtle question that probably wasn't answered before, and it requires knowledge of rational numbers and how to deal with rational powers to make sense of irrational powers. All right, Napiers Constant E. So this is the natural number that you may or may not have seen in the past. It's a special number that comes up quite a bit in calculus, and let's see why. Why does it have any business coming up in calculus? Well, it's related to exponential functions. So here I've got two exponential functions sketched. I've got y is equal to 2 to the x, and I've got y is equal to 3 to the x. Now, if I were to look at the point that they have in common, so that's the point 0, 1. So I look at that point, 0, 1. And what I'm going to do is I'm going to look at the tangent line at that point. So that's the line that just touches the curve at that point and goes in the same direction as the curve at that point, but it's a line. So here's our tangent line. We'll give a more precise definition of tangent line and whatnot in Chapter 2, and this is really going to be the main concept of calculus. But here I'm just sort of playing on your intuition as to what a tangent line is. So we do the same thing over here. We get a tangent line at the same point. What do we notice? Well, we notice the slope of the tangent line to the exponential function of base 2 is less steep than the one at base 3. Here we can work out the value of the slope. It's about 0.7. And over here we can work out the value of its slope. It's about 1.1. And so this begs the question. So I'm only considering two different exponential functions, base 2 and base 3. But there's a lot of exponential functions. In fact, I can take any real number bigger than 0 and not equal to 1 as the base. I have one where the tangent line at that point has a slope less than 1, and another one where the tangent line at the same point has a slope bigger than 1. What's the natural question to ask? We found that for 3 to the x, the tangent line had a slope of roughly about 1.1. At the base of 2, it had a slope of about 0.7. Now what's interesting is 1's smaller than 1, 1's bigger than 1, so there should be an exponential function for some base where the tangent line has slope exactly equal to 1. So here I've got 2.714 is the base, and the slope is still less than 1 there. But if I change the base to 2.732, now I've got an exponential function whose slope is bigger than 1. So there should be a number somewhere around here where the slope of the exponential function at that point has a slope exactly equal to 1. What is that base then? What would the base of the exponential function be? Well, it's got to be bigger than 2.714, but smaller than 2.732. That is exactly what E is. E is that number, so that when you take it for the base of the exponential function, the slope at the point 0, 1 is exactly 1. So let's sketch that. We've got our coordinate system. We've got our exponential function. Y is equal to, in this case, we're going to take the base to be E, where it's this number, and this is an approximation. E is an irrational number. The decimal expansion would have to go on forever. The tangent line at this point, which I'll sketch in here, looks like this. It's going to have a slope of equal to 1, slope equal to 1. So E is defined to be the real number so that when I consider the exponential function of base e, it has a tangent line of slope 1 at the point 0, 1. That's what e is defined to be. It's that number. For when I take it at space as the exponential function, the slope at the point 0, 1 is 1. This is important in calculus because what we're going to be interested in, for the most part, is slopes of tangent lines. And we'd like to have an exponential function whose slope of the tangent line at the point 0, 1 is as simple as possible in some sense. And some of these are 0.7, 1.1. The simplest one would be if we could just find an exponential function whose base is some number so that the slope is 1. And so that's what we're going to define e to be, and it's going to appear quite frequently when we deal with exponential functions because we're going to like to work with the ones of base e due to the fact that their tangent lines have slope 1 at that point.